welcome everyone to this ACM Chicago March meeting. Thank you for being here this evening. We have Volker Mueller, who will be talking about computational opportunities at the digital physical interface in infrastructure production. My name is Alvin Chin. I'm the chair of ACM Chicago. All right, and yes, today is March 17th, so happy St. Patrick's Day to everyone. Hope you're wearing green today. Hope you had a chance to see the Green River. So this year, Chicago did actually color and dye the river green, so that was good to see. We also want to thank members of IEEE Computer Society Chicago. So we've done a lot of ACM Chicago events. IEEE Computer Society Chicago, we've done a lot of events together during this past year. So we thank you for those members to come this evening. If those who don't know, IEEE Computer Society Chicago is the Chicago chapter of the IEEE Computer Society. So IEEE is like the sister organization of ACM, Association of Computing Machinery. We also hold the same topics like ACM. So we deal with software, hardware, computing, AI, big data, and so forth. So I'm also the chair of the IEEE Computer Society Chicago. And our vice chair, Gina Martinez. Here are the links to our social media, our web, and also as well, we also have our previous meetings on YouTube. So if you go to bit.ly/IEEECS chai_YouTube, you will see our previous meetings and webinars there. And if you want to become an IEEE Computer Society member, you can join at the URL below. And slides for this evening will be provided after the meeting. We also want to thank members of Mid-America Club IT Connect. So this is a club, business club in Chicago. They're located on the 80th floor of the Aon building. Normally, when we had events, we would have it actually at the 80th floor. Has very, very good views of the Chicago skyline, but unfortunately, of course, right now, everything is all virtual. So they are also joining us this evening and also our previous events as well. And also, we do the same topics too as well. So the chair is Vijay Konkamala, and I'm the vice chair. If you want more information about the club, provides golf memberships, provide food, so you can have lunch there at the club, or take it to go, or dinner. It's a really nice, high-end, private business club. So if you're interested, you can go to this web pages, or you can contact me if you're interested. And of course, finally, ACM Chicago. So as people know, we're the Chicago chapter of ACM. And if you've attended previous meetings, you know what we do. But for those who don't, we basically hold monthly meetings. So we do this on a monthly basis. And we deal with many different types of computing topics. So we've had stuff on visualization, on AI, on data science, you name it. We've pretty much covered a lot of the gamut of all the different topics. So I am the chair of ACM Chicago. Our vice chair is Mark Temkin, which you can see there in his, looks like some Hogwarts or some type of a castle there. And our treasurer is Greg Newmark with the bean behind him. And so thank you for attending this evening. And if you want to know our future ACM Chicago events, you can go to our meetup site, meetup.com/ACM Chicago. We're also on social media too as well. And we also have our archive of our previous meetings that are recorded at bit.ly/ACM Chai video. And of course, if you want to become an ACM member, you can go to acm.org/membership. Okay, so I'm going to turn it over now to Mark, our vice chair, and he will talk about our next event.
Hi everyone, happy St. Patrick's Day. So after next month's talk, what you see on the screen, you might ask, should I credit my computer as co-author on my next screenplay or novel? Our next presentation with Dr. Melissa Romele will cover existing research on natural language processing and creativity and how this can help write fiction by enhancing an author's creative intelligence. She is a research scientist at SDL.com, which has produced an industry-leading end-to-end intelligent translation solution. She currently works on interactive applications using NLP to facilitate content understanding and creation to augment human creativity in language and storytelling. So make sure you sign up now for this April 21st meeting to be introduced to this truly unique topic. Thanks to tonight's present program, I have learned more about construction and architecture and where it is heading than all the time walking through the living museum of architecture that is Chicago. Our speaker, Volker Mueller, initially an architect, became increasingly involved with software development, focusing on architecture, construction, and design, and has also been a co-organizer for ACM Raleigh, North Carolina. Let's all welcome our speaker, Volker Mueller.
So hello everyone. My talk provides a subjective overview of computational opportunities at construction's digital physical boundary. With computation, I mean involvement of computers, and more importantly, software which needs to be designed, engineered, implemented, supported, maintained, and enhanced. With the subheader, I express my opinion that the history of computer-based computation is closely intertwined with automation, which is strongly driven by the desire to increase productivity. For the purposes of this talk, productivity means producing more while using fewer resources of any kind, including raw materials, energy, and labor. These are my non-comprehensive disclaimers for this talk. Most importantly, this talk is educational. I will not play videos in this presentation. I will show links to the videos on the respective slides. If you're interested, please note them and watch them later. And I think I have a list and we distribute them after the talk as well. Some of them are really interesting and complement the talk that I'm giving here. The goals for this talk are: provide an overview of the globally important infrastructure or built environment domain, and at least for the duration of this talk, invite you to explore this domain with me. Highlight opportunities in the built environment domain for innovation, which requires software-driven technologies. Point out important challenges that software for the infrastructure domain needs to address, and get you interested in solving problems in the built environment using your ingenuity and software design, development, and engineering talent. The disciplines commonly associated with the built environment life cycle are architecture, engineering, construction, and operations. We may generalize architecture to stand for any planning and design activity in the infrastructure realm, whether it is performed by architects or by others. The infrastructure industry transforms ideas into physical reality. It turns ideas into matter. Infrastructure is the human user interface to the planet on which we live. Infrastructure is a contributor to global warming and other environmental impacts and an opportunity to mitigate them. Globally, we are currently experiencing a continuing drive toward urbanization. People are moving into urban centers, searching for better opportunities. They all will require housing, workplaces, and servicing infrastructure. This graph shows percentages of population living and projected to live in urban areas. This is a double dynamic because at the same time, global population has increased and is projected to increase further. Therefore, the need in absolute numbers is increasing even more than the percentages indicate. The UN's World Urbanization Prospects report in its 2018 revision puts our challenge into one number. 2.5 billion future urbanites will require adequate urban infrastructure by 2050, while a substantial amount of building stock and its supporting infrastructure will require renovation or replacement. There is a very specific timeline to this, so progress must be rapid and solutions need to become available at scale within the next decade to affect the imminent future. This often quoted graph shows that the construction industry in the US lags behind non-farm industries in productivity. Most other industries have more than doubled productivity since 1964. construction productivity declined by about 20%. So there is an abundance of challenges. How do we overcome them, and what role could computation play in that effort? Our global software development community is estimated to be 24 million strong. I venture a guess that infrastructure software design and development is a niche, employing about 50,000 of us. While considering various approaches and opportunities, keep in mind that the scalability of solutions is the true challenge. Scalability means size as well as quantity per unit of time. Huge innovative leaps may be required to take what looks like desktop experiments to the scales required in a short amount of time. Historical responses to the scalability challenge have been based on producing more while using fewer resources. This is mostly encapsulated in the term industrialization. In my talk, I will use industrialization and one facet of it, automation, interchangeably. Unpacking the infrastructure industry and its challenges requires its own series of talks. Not just one, but a series of talks. The infrastructure project lifecycle starts with discovery of client needs, moves through design, engineering, and constructability, to delivery, which includes fabrication of object components and on-site construction, including any assembly. Commissioning moves the project into operations, which include maintenance, remodeling, and renovation. End of life cycle is decommissioning and demolition with recycling of components or materials. There are various design and engineering disciplines involved, and contractors and their subcontractors turn plans into physical objects. I will describe opportunities at various junctures of this life cycle and along various of the integration axes, not necessarily pointing them out explicitly. Early this millennium, in 2003, Stephen Kieran and James Timberlake speculated in their book Prefabricating Architecture about how manufacturing methodologies are poised to transform building construction. They reference very strongly automotive and aerospace manufacturing. One reason is that the automotive industry brought us all affordable cars. This shows a production line for the German Volkswagen Beetle from the middle of the past century, and some of the workers assembling cars. The workers vanished from this picture and automation entered in the form of robot arms. Robot has its etymological root in the Czech word robota, which also means drudgery, indicated here by the robots taking on highly repetitive, drudgy work. The reference to aerospace is because of the size of objects. Airplanes are perhaps the largest objects being assembled in sizable numbers in a factory. This image shows the Boeing plant in Renton. An early experiment in industrializing the building process was attempted at the Hufeisensiedlung in Berlin, designed by architect Bruno Taut and constructed from 1925 to 1933. In the horseshoe part, it is visible how construction was semi-industrialized by a sequential process working its way around the horseshoe. This type of industrialization at the delivery location was not successful and did not evolve into an established construction practice. Another example of industrialization was the prefabricated Lustron house made from steel, actively sold from 1947 to 1950, when the company went bankrupt. Houses sold about 25% below the cost of a comparable home. However, each house had been sold at a loss. The kit of parts was flat packed and fit on a single truck. Even the Lustron home had to be assembled in its final location, unlike cars and planes. Infrastructure object construction has stubbornly remained sticky to location that way. You may wonder, so what about mobile homes, which are so much more like cars and planes? Archie Graham suggested in the 1960s the plug-in city. Folks would move with their residential pods from one plug-in city to the next. What happened is that there is a stigma associated with mobile and modular homes. iconographic was a depiction of the stacks from Ready Player One. This image resonates with us because it caters to any prejudice we may have about mobile home parks. Since Lustron Homes and Plug-in City, modular construction has come a long way. This photo shows Marriott's AC Hotel in Chapel Hill, North Carolina, under construction in 2017. The modules are manufactured by Champion Commercial Structures. There are construction videos at the AC Hotel Chapel Hill Facebook page. And nonetheless, location is still sticky as expected. Construction time on site, though, is significantly reduced once the site and any in-place structure had been prepared with traditional methods. This looks like significant progress in terms of industrialization. Behind the scenes, the modular construction process is still a largely manual process, like the Volkswagen assembly line from perhaps 70 years ago. The progress made is that a large part of the construction process has moved into enclosed spaces, making it independent from weather. Workers can perform work in a much safer, controlled environment. The question is, how will this change in the future? About the location dependency. Infrastructure projects are mostly singleton projects, each needing to meet its own requirements. Most projects are subject to their individual design and engineering efforts. As example for regional impacts, I show the US maps of climate and seismic zones, which affect infrastructure design, engineering, construction, and operations. In addition, each jurisdiction has its own building codes. Regional delivery frequently means that there is a new or significantly reconfigured supply chain for every delivery. There is a varying pool of workers with varying skills. Finally, most infrastructure objects would be too large to construct in a factory and then to transport them fully assembled to their delivery locations. When we think about automation, we think computing. There is a familiar example of automating weaving, the weaver's looms, and jacquard punch cards. You all may be familiar with the term computer, originating as human profession when transferred to machines that replace those computers, or then transferred to machines that replace those computers. The organizing group for this talk is the ACM, which is the Association for Computing Machinery, founded in 1947, only a few years after the first electronic computers had become functional. Early impact of computation in the infrastructure industry was through digital design tools. The goal was to increase the productivity of design teams. Electronic drafting accelerated drawing production. Next were three-dimensionally oriented design tools like FormZ from Autodesk, where I contributed to software development from 1993 to 1998. Goal was design visualization to assess aesthetic performance. Interesting looking projects sell. While support of three-dimensional modeling has pervaded the infrastructure design and engineering disciplines, a challenging frontier is to enable designers to design in space. A spin-off from research at the University of Montreal is Hive 3D by Thomas Dauter and Michael Hoffman, enabling immersive design in 3D space. There are several videos available on Vimeo or YouTube. There are other tools out there like Gravity Sketch. Their modes of interaction are different from Hive 3Ds. How does the user experience with those physical UI gadgets compare to the user experience of interacting with real physical matter? This is a screenshot from a video showing 3D modeling and infrastructure design using a tool called VR Sketch. VR Sketch works with SketchUp, which was owned for a while by Google and distributed for free in an attempt to populate Google Earth with 3D buildings as a global community project. So in the last few slides, there are several stories. One, truly intuitive 3D modeling is a tough problem. Two, creating a 3D model of all infrastructure objects on Earth is a tough problem. And three, virtual interaction with three-dimensional virtual objects remains awkward And making it less awkward is a tough problem too. This is an almost seamless segue to reality modeling. Reality modeling means creation of a digital one-to-one scale model of the real world, preferably geo-referenced, which means that the model is fitted into a virtual model of Earth at its accurate location, orientation, and elevation. Google's aborted community project of modeling the world's infrastructure became obsolete due to other technologies that have evolved rapidly and are populating Google Earth and Google Maps. Mark mentioned LiDAR in one of the advertisements for this talk. LiDAR is one source of 3D models for reality modeling. LiDAR samples range data based on the travel time of the sampling laser. LiDAR sampling of large areas is usually done from the air. This generates three-dimensional point clouds with varying densities. Other sources for reality modeling are photos, videos, or GIS data. Until about a decade ago, generating 3D data from photos was a process called photogrammetry, performed by humans. This process has been fully automated. These processes generate point clouds of varying density, the photo-based ones also including color information. A textured surface model can be computed by fitting the point clouds in a computational process. Progress in computing speed, decreased cost of memory and storage, and cloud-based parallelization of processes has made these computations feasible. Important is that these data can be geo-coordinated and calibrated to actual measurements so that planning in this context can be done with high accuracy. This image shows a 3D model created by Context Capture, the reality modeling tool from Bentley Systems, where I worked from 2008 to 2019. Lateral integration in infrastructure design and engineering is based on a building information model, short BIM, that combines accurate 3D model data with disciplined business data. This supports cross-disciplinary collaboration and coordination during design and construction. Clashes between systems are either entirely avoided or discovered before construction starts. The discipline models support discipline-specific performance evaluation, so that there is no need to maintain parallel models which tend to diverge over time and introduce errors. This way of working at its best is integrated project delivery from design through delivery. The disciplines models also include skin and interior fit-out, now extending beyond visual analysis of aesthetic appeal in support of a multitude of building performance evaluations. The structural design and detailing software Tekla by Trimble is an example for how software can support the integration of the information flow from design through analysis to the subcontractors who will be responsible for fabricating and erecting the structure. I mentioned Tekla because our software Raptor uses Tekla's API to extract part information from Tekla's building model. From that information, Raptor computes how to fabricate the part. Another relatively recent development in infrastructure design is computational design. Most often, computational design is now understood as providing a graphic programming interface to a 3D modeling system in order to set up a, I'm sorry, here's something is bothering my phone. So most often, computational design is now understood as providing a graphic programming interface to a 3D modeling system in order to set up a parametric design system for an infrastructure object, in this case, a bridge. Computational design systems allow designers and engineers to implement object behaviors, design and engineering constraints, and constructability considerations into the design systems. The resulting design is more likely to meet these constraints and will not need a lot of revision before it is constructed, accelerating design time. Some of these parametric design systems work cross-platform, like this integration of 3D modeling software Rhinoceros from Robert McNeil and Associates, with its graphic programming interface Grasshopper connecting to Tekla structures. The desire is that beyond integrated project delivery, BIM data sharing extends along the entire infrastructure object lifecycle. The graphic from infrastructure software vendor Autodesk illustrates that the object lifecycle could become a true cycle. Its hub would be a well-maintained building information model, or perhaps a built environment model extending across all infrastructure object types. Such well-maintained built environment model is now commonly dubbed a digital twin, enabling what-if scenario testing in a non-destructive and non-disruptive fashion. Infrastructure objects have a long life cycle. Consider the data maintenance and validation challenges. What opportunities? Obviously, general software challenges like usability, accessibility, data security, data longevity, and others apply as well. This is also where the Internet of Things comes into play. Embedded sensors can provide feedback about infrastructure objects, and embedded controls can control their behavior. Combined with artificial intelligence, our built environment can become really smart. This is certainly another set of frontiers. Proper segmentation of unstructured scanned 3D data into discrete objects is another rapidly moving computational frontier. Combining and validating the design data in a built environment model with scans of the as-built situation is part of that opportunity space. This may start during construction to monitor construction progress and any deviations from the plan. Collection of the data is often done with drones. Flight path and photo location planning is another frontier for computation. If the as-built data are accurately maintained, hidden objects like service lines hidden in walls or underground could be made visible in augmented reality displays. Let's talk about how we get from the design, engineering, construction model to the physical, built or installed object. This is the area of automated construction technologies. I will describe 5 developments, one as a method mentioned earlier, and 4 centered on materials because they highlight the challenges in this domain. That's modular construction, and the materials masonry, concrete, steel, and carbon fiber as an example of a non-traditional construction material. Modular construction is one area in which construction industrialization approaches the current frontier of where digital design hits the not yet automated material world. These are snippets from recent research by Tom Greenough and others titled Integrating Computational Design to Improve the Design Workflow of Modular Construction from the International Journal of Industrialized Construction. Shown are several software-driven areas. Computational design that embeds constructability constraints, a building information model that extends the geometric description of a project with business information, analysis software that validates the design for various requirements, like structural soundness, and automatically generated documentation for construction. We see in that image snippet that the last step is still manual construction, as I had discussed earlier. As will become clear, the biggest frontier in construction automation is an amalgamation of challenges. Dexterity is one. Flexibility is another one, recognizing any situation and quickly adapting one's behavior to it. Frankly, intelligence is what is often required in construction for what may be inaccurately considered menial tasks. From here on out, potential for AI applications is implied. In addition, for all the automation processes described next, there is some software converting built environment information into instructions to some sort of machine, including robots. This is the digital physical boundary in the title of my talk. Here, the digital meets the physical. It is also the area where collaboration between discipline experts is required to succeed. This goes beyond understanding business processes. It requires some level of understanding material behaviors, mechanical systems, control systems, constantly pushing into the unknown and how they all interact. Because infrastructure is three-dimensional, a good grasp of geometry helps. In German we say, keine Berührungsängste. Don't be afraid to touch. This image from the International Journal of Industrialized Construction distills the challenge to a perhaps polemic point. However, construction sites look like this. Of course, for various reasons, this type of challenge is being actively researched and responded to. This is a screenshot from a video about Boston Robotics Spot, a quadrupedal robot for challenging terrain. Katerra is a company that integrates horizontally, vertically, and laterally, and leverages the advantages of this integration in its modular manufacturing facilities. Unscientifically requoting from Bloomberg through Archinect, the company's mission is to shake up the construction industry with a combination of efficient factories, prefab parts, and modular construction units. The note tells us that at the end of 2019, Katerra announced it would close one factory and shift manufacturing into a highly automated, lower-cost factory elsewhere. This means that automation has arrived in modular manufacturing. We will revisit this in a few minutes. Here is an abrupt transition to materials. Masonry. The Swiss researchers, university professors and architects Fabio Gramazio and Matthias Kohler pioneered automated bricklaying. To avoid the messiness of mortar, they chose to glue the bricks. Their pioneering work tackled the issue of how to convert some target building geometry into instructions to a machine to achieve a very specific result. The frontier of bricklaying with proper mortar joints has been crossed, as the video available under the displayed link will show. Note that the machine requires 2 human workers to ferry supplies to it and clean up the joints behind it. Fair enough. Its name is SAM for semi-automated mason, devised by a company named Construction Robotics. A more direct path from a building design to a masonry home is taken by the masonry robot Hadrian X from FBI in Australia. The brick layout is computed from the digital building model and translated into instructions to the robot. The bricks are stacked using a special adhesive. Reinforcement bars, rebar, added manually by human workers, and then the cavities in the bricks are filled with concrete. Hadrian X automates and accelerates significantly the bricklaying part of the construction process. Thinking about scalability of approaches and regions of need, in their latest video, FBR shows 2-story bricklaying and mentions how it may be applicable in countries like Mexico or in regions like the Middle East, which have many attached 2-story developments in masonry construction as their regional response to housing needs. Transferability of technologies and scalability are beautifully captured in this image that I grabbed from the World Wide Web almost arbitrarily. Inadvertently, it makes a statement about the challenges and opportunities for 3D printing in the infrastructure industry. This is a segue from the material masonry to the material concrete. Concrete being pumped to its installation location looks like 3D printing. Construction concrete is a rough material containing sand and gravel in varying sizes. Concrete tends to slump and needs to flow into all the nooks and crannies of the formwork, passes through rebar cages, etc. This stuff is not what anyone could use for 3D printing. Consequently, this type of technology transfer requires a substantial amount of material research to develop a 3D printable version of the material that still meets all other requirements of the target object. I guess because of COVID-19, I'm not really used to talking that long in one piece. EPISCore is using a concrete mixture, and in the video under the link shown above, they appear to indicate multi-story buildings coming soon. They print hollow walls. Similar to the stacked bricks by Hadrian X, they will be manually reinforced and then filled with concrete. The printed parts are lost formwork, erected at a much faster speed. EPISCore's printing mechanism sits on a rotational base that can change its height and has a printing arm that can extend out. In contrast to Episcore, which prints its buildings on site, Mighty Buildings prints their buildings in their factory and delivers them as modular buildings to the site. This is a hybrid approach. Perhaps plug-in city is yet to come. Mighty Buildings uses a composite material reinforced with glass fiber that is hardened with UV light. Working in a controlled environment has the advantage that the amount of UV light can be controlled very accurately. You may have noticed that they use a 3-axis gantry system. This approach to automating modular construction uses a fundamentally non-traditional construction method using non-traditional machinery and material. Some of the work is still performed manually, like the structural insert visible in the screenshot and later fit out. Combining the automated processes with the opportunities of computational design will also allow mass customization. I'm not sure whether you're familiar with that expression. Mass customization means that instead of many identically looking modules, it becomes feasible to generate populations with individual expression. So each individual looks different. This could counteract the otherwise threatening monotony of mass-produced objects. With this example, we have moved from 3D printing with concrete to printing with other materials. MX3D developed a process to 3D print steel objects of considerable size. In the video under the link, MX3D's Joris Laarman describes the potential of the technology they are developing. They are using a process similar to electric arc welding to deposit steel from a wire reel at the locations determined by their metal printing software. This promotional slide from one of the project partners, Lenovo, illustrates the vision that the technology could provide its own scaffolding. It also illustrates project partner Autodesk's idea of generative design, which proposes a computational approach toward material optimization based on meeting computable performance requirements. In this case, structural requirements and perhaps manufacturing constraints. Steel is an interesting material. According to the American Institute of Steel Construction, AISC, steel produced in the United States contains 93% recycled steel scrap, and 98% of all structural steel is recycled at the end of an infrastructure object's life cycle, with no loss of its physical properties. As such, structural steel can be recycled virtually indefinitely. Okay, I had to get that plug in because I am now part of the structural steel supply chain. Steel coming from the mill has an allowance for dimensional variation to which a machine needs to be able to adjust without creating a failure. Processes need to be defined in a way that specific dimensions are maintained with high accuracy, independent from imperfections of the material. The photo shows side by side two beams with the same nominal cross section, and they exhibit significant differences in actual dimensions. The machines that drill and mill structural steel are specialized machines. They are developed for the heavy-duty task of modifying the steel received from the mill. Substantial forces need to be applied when processing structural steel with the desired production speed. Therefore, these machines look different than the other robots. Nonetheless, they are computer numerical control or CNC machines like the other robots. In the case of the steel fabrication equipment that our company, Peddinghaus Corporation, manufactures, the software converting geometric design information into instructions for the machines is Raptor, developed by our software development team. From Tekla's structural building information model, we retrieve part information directly through its API. This closes the data flow gap from digital design and engineering to physical fabrication. The CNC code generated by Raptor instructs the machine, and the digital turns physical. In terms of scalability, Many steel structures in the US and a sizable number worldwide contain structural steel processed by our machines. The next step is to assemble these structural steel members on the construction site into the structural system of some infrastructure object. This is one of the next frontiers for automation, and the challenges for all sorts of machine or robot designers, engineers, and programmers are highlighted in this photo, perhaps with some hyperbole. Change of material, carbon fiber or other filament. University of Stuttgart's Institute for Computational Design and Construction, ICD, under the direction of Professor Achim Menges, designs and constructs experimental pavilions on a regular basis as part of its teaching and research program. Several of the pavilions were constructed from filament or fiber. The video under the link describes the ICD ITKE Research Pavilion 2016-17 project. The process involves a drone passing the filament back and forth between two robots. The video also indicates that this project required specific software to analyze the structural behavior, to plan the fabrication process, and to coordinate and instruct the machines and people involved in the process. I am hypothesizing that the Pavilion project may have been inspired by Tester and Weiser's speculative projects Carbon Tower from 2001, Filament Tower, and Strand Tower from 2006. Given the premise that the tower is constructed from filament, a flexible material combined into something like a monocoque structure, there are several challenges that come to mind, with perhaps the most challenging being design and analysis software. Design and analysis software needs to be developed that supports and analyzes the behaviors of the material and the resulting structural system. A construction process would need to be invented that keeps the construction worker safe and the structure sound throughout all phases of the construction. Construction machinery would need to be developed that is able to execute the proposed construction process. Software would need to be developed that generates the instructions for this machinery. A thorough discussion of this project is available under the video link shown on the slide. These future construction materials, methods, and their required machinery could be inspired by existing technologies like climbing formwork, commonly used to construct mostly linearly extruded service shafts in high-rise buildings constructed using pumped concrete. Or this type of knitting machinery, which interestingly enough is a double jacquard machine. This way, we have come full circle. This may have been a bit of a roller coaster ride. Well, even a roller coaster is an infrastructure item, and nowadays even roller coasters are designed with software and eventually fabricated and erected. This specific roller coaster is the largest mobile roller coaster in the world and one of the biggest attractions at the Oktoberfest in Munich. Well, hopefully we can make it then this year after we got through COVID-19. This was a transact through the frontiers for software development in the infrastructure industry, which is where digital data need to be transformed into physical objects at significant scale. I hope that I inspired some of you to pursue any of the challenges that I pointed out. This is an industry with direct impact on the physical world that we inhabit, with opportunities to improve the lives of millions of people by providing better places to live, work, and move through our world. Certainly, I'd be happy to talk with anyone interested in what my team's current and future challenges are, to which we need to find robust and reliable solutions. I hope you all enjoyed this talk and are taking something away from it that is relevant to you. Thank you all for your time.
Okay, great. Thank you, Volker. So we have time for some questions. So please type them in the Q&A, and Mark will read the questions then.
Okay. Well, I've got a question to start things off. Volker, do you think as these techniques become more available, will the kind of architecture chosen be more modernist or would it tend to be emulating in quote traditional designs?
This is more of a philosophical question. Ultimately, the machines and the software don't care, right? Um, I don't think that there is an implication. Um, if you search on the net, there are examples for rather Baroque-looking fabricated stuff. And that's possible, right? I mean, now we can suddenly fabricate objects with high level of ornamentation without really causing additional cost, right? Because nobody has to hand carve or hand plaster or whatever, right? We just let the machines take care of it. So it just then becomes a computational expense. You know, how do you create maybe interesting and non-repetitive or well proportioned ornament, right? I mean, that's a computational task. People would have to figure it out. I know people have experimented with that. So ultimately, the software and the systems won't care whether they fabricate a straight line or some spiral or rocaille or whatever rococo type baroque ornament. So no, I don't think that there is any implication in that direction, which may be good or bad. I really want to stay neutral here. I'm a modernist, so there went my neutrality.
Sorry about that noise. That was my whiskey bottle. Unfortunately, not. Fortunately, Scotch, not Irish. All right, we have another question here. Can Volker comment about the possibility of these technologies in reducing the cost of building non-replicated buildings? In other words, will fully custom building design become more affordable? This is from Neil Ormos.
Yeah, that is also a very good question, right? In my talk, I indicated, okay, the industrialization and automation of automotive production makes affordable cars available to us, right? And I, certainly, I wanted to hint at that possibility. So far, that hasn't really materialized. Ultimately, you'd have to really look at how much or how little the pure construction cost contributes to the construction, to the overall infrastructure object cost. There was recently one example where a bridge, I think, cost like 1.6 billion, and the cost of the concrete used in it was a couple of 100,000 or something. I mean, really, the costs are elsewhere, right? If you want to build a house, you have to pay for financing, you have to pay for the land, you have to, and those costs add up. And the materials and the construction really are not that big of a factor in there. My hope would be, yes, that we benefit from that. So far, that's really not shown, at least. Maybe that's because the traditional construction is so routine that it will remain competitive for quite a while. At the large scale, I think automation has a real challenge, right? If you want to build a high rise here in Chicago, how much of that can you realistically automate in the next 10, 20, 30 years? I think we are hitting a challenge there that has to do with the scale of objects, the weight of objects, all those types of requirements, which will be very difficult to overcome.
So I have a question, Volker. In regard to like, what do you see the future of construction going to be? Like, for example, do you see like I see, for example, the certain like examples where certain particular components or so are already prefabricated, beforehand, and then they just bring it to the construction site and then just kind of modular. Like think about like for example, Lego, right? You have Lego bricks and just kind of have something componentized, or like for example, IKEA, right? When you buy IKEA, products or furniture, you already have certain things that are ready, pre-done, like components, and you just kind of put these particular components, together to form whatever you want to create. Do you see that kind of this kind of modularization or so, more of that going to be happening in the future for construction?
Where it is happening is, if you look at modular construction firms and so on, it seems to really happen in the hospitality space. The example that I showed is not the only hotel that got constructed in that way. One of the fabricators that I looked at, they have been constructing housing in South Dakota, right, for the oil boom there. It certainly there is an increase of that. Again, on the other hand, I somewhere that's anecdotal, saw that a mortgage lender, refused to finance a house that was built using modular construction, because again, it has that stigma, the architects that wrote that book, they did an experiment with modularized construction, more like a prefab kit of parts, closer to the Lustron home example that I showed. And that was a relatively big house, and it was not an affordable house. And certainly, doing it in a low series, or maybe just as a singleton, you won't get the cost benefit to begin with. So overall, in certain types of commercial construction, it's definitely increasing, and that's and then there are regional differences. So in Germany, for example, a lot of the single family homes are done from prefab parts. So you put the slab in the ground, and then they bring the walls and they put them together. And nonetheless, those designs are relatively highly customizable. They just prefabricate the part the parts in a controlled environment, and that already gives them a high benefit of they can do that while the site preparation is in progress, right? So they can parallelize this production process. They are weather independent. In Germany, that's a factor. In some regions of the United States, it would be a huge factor. And all of those things contribute to containing cost. So it's practice there. Again, here, the thing is that the normal stick-built construction, the developments that go up outside in Chicago and elsewhere, they are just still highly cost-effective because of relatively cheap labor, of known processes, of not highly innovative architecture, all of those reasons. And again, it takes a certain size of operation to even industrialize a process. A lot of the builders are not big enough to do that. Catera did it. They were a startup. Silicon Valley executives started that company and started it based on venture capital funding. So it's an entirely different premise. Most home builders are, they have their established practices, and that's how they work. And so some changes will occur, but innovation in the whole infrastructure industry has been relatively slow. It's a relatively slow industry because there's a lot of, there are a lot of smaller operations. I talked about the always changing local supply chain chains for projects based on their location and so on. That makes it very hard to automate the way the automotive industry has done. If you look, how did that happen? Well, they have a big factory somewhere, and then they have their ecosystem of suppliers around them. They have well-established supply chains. They do just-in-time delivery. They spit out cars on one end, right? At one end. On the other end, the parts come in. It's a whole different process. So it's just very difficult to transfer that approach to buildings. That's why I mentioned in the end the carbon tower, because maybe we have to think about what can work in the infrastructure industry in a different way, because there are just different boundary conditions to which we need to be responsive.
Okay, well, we have a few more questions if you don't mind. Here's from Simon. How might the industrialization of the construction industry affect smaller businesses that could not afford this machinery? Who would be the major players then to watch out for in the future?
Well, that's a good question. There are certainly large contractors that have done automation. I think Lang or O'Rourke in the UK, they have built a factory, because large contractors certainly have this capability. Most likely the large contractors here in the United States, I don't know for sure, so I would throw out just names, but so large contractors in the United States, and I don't want to offend anyone by not mentioning him or her, companies like Mortons and Turner, and see there are many more. Skanska, who else? Well, they all look at that. I strongly believe that, and in parts it has been I don't know which one of them, but they are assembling modules, like if they have a building with a high number of services, like a hospital or lab building, where they essentially install the services in cages, so all the piping and wiring and so on, and then slip fit it together in the building. But that way they reduce the on-site construction time, and they can modularize that in transportable sizes. And they, because they do it there on the shop floor, they can get very clean installation. It all aligns. They have no conflicts. It's not the sprinkler guy coming through and throwing out the HVAC because it's in his way. All those types of things just don't happen then, because it's all done in ultimately in a shelf on the construction, on the shop floor, and then brought into the building, usually put together with slip fittings or other ways of connections, minimizing the time on site and maximizing the advanced coordination between those systems. That's all going on for larger projects. That wouldn't work for a single or multi-family residence. So they certainly look at that. There are multiple factors driving that. One is certainly cost. Another one is that the construction industry has been challenged globally, ultimately, to find new skilled labor. They have a problem attracting people. And so there has been a labor shortage in the construction industry. Perhaps not currently seasonally and because of the pandemic, but ultimately there is a skilled labor shortage in the construction industry, and that also drives that automation, because how else can they satisfy the demand? And I kind of pointed to one dimension of that demand. How can they satisfy that if they don't have enough laborers? So that's where they are really also pushed to automate.
We have our last questions here. I'm going to group two of them together. So this is I'm combining from Matthew and from Mike. How do you convince an industry that outside of fairly large projects with forward-thinking general contractors is still very paper-based to move to digital modeling-based workflows that would enable more automation to be performed? And specifically, are you using commercial 3D modeling software, or is it customized?
Okay, so that were multiple questions. I'm not, is the question about going from paper to digital, is that about any participant in the construction industry, or is that just any industry?
Uh, Looks like construction. Or
In the construction industry, that has been a slow process, right? I suspect there are still, some contractors out there, and perhaps also some architects at the other end of the process, who still draw on paper and do small projects, and that's just fine. There are people that still believe the fax machine is the high end of technology. As long as they can make a living from that, I think that's okay, right? So some of that change will be generational, will be, as I said, we started talking about 3D, three-dimensional design in architecture. When I joined the program at Ohio State University, they had been already talking about it. I joined it in 89. That transition was still going 20 years later, right? So some innovation just happens very slowly. Change management seminars are usually good in saying, okay, when you're back in your office, get up, look around, and just understand that, many of those people are the people that will still be working there 10, 20, 30 years later. So how do you get them to change, right? Some won't. They, at some point in time, it'll be a generational transition to make innovation happen. The other thing is those smaller operations, they don't have the knowledge, the time to acquire the knowledge. They might not have the financial depth to acquire the technology, all those types of things. So they are slow to change, right? That has been one of the problems in the construction industry, and probably also has influenced the way the productivity has developed. There might be other drivers of it, because one would think that we as an industry should be able to at least stay level, but instead it declined since '64.
I guess, and just the end of that question was, are you using commercial modeling software, or is yours customized?
Well, so I'm I'm directing the software development team. We are developing our own software. This is our own software. So I think that makes it customized, but we are distributing that software with our machines, right? So it's a commercial software. So I don't know where this question is going. So we are developing commercial software.
Okay, I think that answers that question. And for the final question, this is from Bruce Montes. He says, "Thank you, Volker. And do you believe that there's a near threat to labor with automation in these areas which will create resistance to adoption? Or is this something that is much further away than, say, in some other industries such as transportation or food production?"
Well, you are welcome first in response to the thank you. Well, that's a difficult question. I kind of skirted along that question in my talk, I think. And I took out some comments that I had in the talk, also because I needed to keep it shorter, talking about it. Whenever technology proponents talk about automation and labor, one way to put it is, okay, we are enhancing the capabilities of people to be more productive. That goes back to what I said about change management, right? Look around, and do you think that the people that are there doing the job now, when some automaton comes along and takes on that job, what will that person do? Is it possible that they get retrained to be a software engineer who starts developing software for that automaton? Or what will they do? It's that's why I pointed to the labor shortage in construction. That might be the way out, right? Saying, well, we are facing a labor shortage anyway, so we have to complement our labor force with robots and machines and all that. But personally, I think that if you look at statistics, the jobs in manufacturing have declined, in farming even more. So that farming, you can tell, has become more and more industrialized. Fewer farmers produce more stuff. The job growth has been in service industries. Now, what are service industries, right? That's a big, big, big area. Reaches from somebody, I don't want to denigrate it, but that's kind of the stereotype, right? From somebody flipping burgers to somebody advising other people on their $1 million portfolios, all service industry. So my suspicion is that the Mason that with highly evolved experience and skill makes a beautiful brick wall. Now the robot comes along. That Mason, if he or she is lucky, will be carrying the bricks to the robot or cleaning up the joints after the robot, or setting up the whatever guidance system that robot needs, if he gets uptrained to do that. So suddenly, people will lose their skilled job and become what we call the Handlanger in Germany, essentially auxiliary service, labor servicing the automaton. That certainly lays down bricks at a faster pace, right? So that semi-automated Mason is about 3 times as fast as a human Mason. So there's that aspect certainly. I don't know. There are no clear answers, right? Optimistically, we all think, oh, they find good jobs after they have been replaced by automation. Pessimistically, it's like, well, we'd have to look at them, right? It's individually, if they have been in the business for 30 years, they are older. Are there people who would be willing to retrain them for other jobs and so on? It's a big question. I don't have a solution.
Okay, great. Thanks, Volker, for answering all those questions. Not always easy, but always interesting. So, thanks again for your great talk. And we're just going to remind you about next month's program. And of course, then we're going to go to our special photo taking session of everyone wearing green or near green. And again, remember next
and
month.
also maybe and also as well and also as yeah and also as well I'm going to launch, there's a poll here, so you can complete the poll
Right,
as well.
right. We need your advice. Uh, and so next month again, about 4 weeks from now, April 21st, Melissa Romiley, I think I got that right, but I'll find out, and natural language processing and computational creativity. And who knows, it might help you become the next, pick your favorite potboiler author, or better, someone in literature. Again, this is about enhancing your ability, not doing it for you. And following April, we are going to have, as you can see, to be announced. We will have a new program in May and, of course, in June. And so thanks for everyone who's come, and glad for a lot of people sticking around for the questions. I know that was a really interesting program. And of course, remember, we are looking for speakers and topics which could be you, and just, let us know. And if you don't let us know, we're looking for you.